In our last lecture, we introduced you to PIM Protocol Independent Multicast and PIM Dense Mode in detail. It is time now to move over to PIM Sparse Mode. But PIM Sparse Mode is very much unlike PIM Dense Mode, where it's going to take more than a single lecture to cover all of the aspects of PIM Sparse Mode. So we've broken it down into an introduction lecture, which is this one, and then one lecture with all of the details. So today what we want to actually learn is the overall ideology of PIM Sparse Mode, what it intends to do, how it intends to do it, what are the various mechanisms that come with PIM Sparse Mode, what are the various entities of PIM Sparse Mode, but not necessarily the packet level details. That would be the content of another lecture. Now, PIM Sparse Mode addresses many of the scaling issues that you encountered with PIM Dense Mode. So the first major difference, that whole idea of implicit join, that you just pretend that everybody needs a copy of that stream, every single router in your network, which PIM Dense Mode did, it is now discarded. It's gone away. So the idea now is that a receiver must explicitly choose to join a multicast stream before one is delivered to them. So in that way, if PIM Dense Mode was a push model, I'm going to push all of the multicast stream to the remote corners of my network. PIM Sparse Mode can be referred to as a pull model. You need to have a router that is attached to a receiver pull the stream towards it before it actually can deliver that stream to the end receiver. Now, they do share names, PIM Dense Mode, PIM Sparse Mode, but they're essentially very different protocols. They have different priorities. They definitely have very different mechanisms. Now, they do share some packet formats, which we will be discussing in a different lecture. But for now, I may go back and forth comparing PIM Dense Mode to PIM Sparse Mode, but they are and remain very, very different protocols. Initial signaling. So the end goal for PIM is to bring the sources traffic. So there is a multicast source that is creating traffic or generating a stream, and there are interested receivers. The end goal for PIM Sparse Mode is the same as any other multicast routing protocol. It is to get that traffic from the source, but only to the interested receivers. So the first step, as with any other multicast routing protocol, is to locate the sources and locate the receivers. So it's important to go over how the sources and how the receivers actually first do their initial signaling, inform the multicast network about their existence. The sources, they signal the first hop routers. So FHR, if you have forgotten that particular lecture or if you haven't seen it already, I highly recommend you go back to it and actually see it. But FHR means a first hop router. These are the routers that are directly connected to multicast sources. So multicast sources must inform the FHRs, which are basically their gateway into the multicast network, about their existence. Now, this entire act happens completely in data plane. And what really is happening, the source is going to send a multicast packet. It is an IP packet with a multicast destination. And as long as the FHR is a multicast enabled router, it is going to process this packet. It is going to realize that this packet happens to be a multicast packet, and it is going to look at the source IP address of that packet, and it can create an S, G state because it has both of those pieces of information completely in data plane just by processing or capturing that packet. So source signaling, very easy. Receivers, on the other hand, will signal the LHRs, or the last hop routers. Now, just like FHRs were directly connected to sources, these routers, the last hop routers, are directly connected to multicast receivers. And just like the sources, the receivers must signal to the LHRs about their existence. Now, we have done separate videos for both the source signaling and the receiver signaling, so I'm not going to go over a lot of details there. But ultimately, the receivers need a little bit more than just data plane learning. So there is a protocol called IGMP, or Internet Group Membership Protocol, that is used by the receivers. Or on the other hand, if you already know that you have some interested receivers, they for some reason cannot perform IGMP, you can always, on most implementations, statically program a receiver on an interface, and this would be via router configuration. So there are a couple of different ways of doing it, but ultimately the FHRs should be aware of the sources and the LHRs should be aware of the receivers. So now we are going to discuss actually what the network looks like once the initial signaling happens. So what is PIM Sparse Mode's challenge? Like any other multicast routing protocol, it needs to connect the FHRs, which are purportedly connected to sources, to the LHRs, which are purportedly connected to the receivers. That is their definition, so we need to connect the two of them. So here is a receiver in our network in the lower right-hand corner, and here is a source. Now between these two is going to be an actual multicast network. So this is just a network of multicast enabled routers. They are all connected to each other, and routers R1 through R7 can run some sort of multicast routing protocol. They may also be running unicast routing, but in this case, let's assume these are all PIM Sparse Mode routers. Now, pay attention to the legend on the left-hand side. So all of the orange arrows, that is the actual multicast traffic. That means these are the packets that have multicast destination IPs and unicast source IPs. And the light blue color, it's the IGMP signaling that the receiver should be using. So let's go ahead with the source. The source is going to send a packet to a group. So now this G is really just a multicast destination. The S is the IP of the source. So it may be that the IP on that particular interface right here, or it could be any other IP, but ultimately that is the IP that R1 would see. Now, once R1 receives this traffic and it can actually process this traffic, it can create that S, G state. So once again, if you haven't done the prerequisites for this particular lecture, that would be the multicast routing protocols and multicast routing protocol routers and receiver signaling and source signaling. But right now, we're just going to skip all of those steps because they have been covered in another lecture. So R1 has an S, G state. Similarly, on the bottom right-hand corner, this receiver is going to signal via IGMP to the two last hop routers. So R5 and R6 both happen to be on the same subnet. They are both receiving the same multicast stream, and this is just a linked local multicast stream on IGMP. And they both receive it and they both process it. And what does the receiver want to do? It just wants to join a group. So it doesn't really know the source yet. There is the use of your wildcard. It is a star, G join because it wants a stream that comes on that group, G, but it doesn't really care about the source. If any source happens to send on that stream, that should be delivered over to the receiver. So after this initial signaling, once the multicast traffic has been received from the source, the IGMP signaling has been received from the receivers, there are two states in this network. On R1, the FHR, you have an S, G state. And on the two LHRs, R5 and R6, you have two star, G states. And that's all that happens after the initial signaling has taken place. The next piece here is really the central crux of PIM Sparse Mode. And this would be the concept of the rendezvous point. Let's recap what happened on that last slide there. The FHRs now know about the sources. In our case, there was a single FHR. And the LHRs, which we had two of, know about the receivers. So they have these multicast states from the source and the receiver. Now, if they could just somehow share this information, they could start connecting the source to the receiver, which is the end goal for PIM Sparse Mode. One of the ways could have been that they send this information, the state information, to each other directly. Either the FHR sends it to the LHR, or the LHR requests it from the LHR, or the LHR pushes it to the FHR. Many different things could have been done there. Think of the scaling nightmare on many different levels. It is literally a scaling nightmare to the level of PIM Dense Mode. What happens if an FHR is also an LHR? What happens if an LHR doesn't really need that information anymore? What happens if an FHR just goes offline? How do you keep track of a new FHR that has now appeared in the network? So really not the best idea there. There is a simpler solution. Think of a central registry. Well, this Rendezvous Point, this happens to be that special registry. It is also called the RP, and for the rest of the lecture you may not hear me say the word rendezvous anymore because of obvious reasons. So RP from this point on. And what is the idea? It's extremely simple. Pick a single multicast router in your network. So the only stipulation here is that the router should be multicast enabled. It should be part of the network. It should be connected to the other routers in the network and running a multicast routing protocol. And you assign it some special duties. In fact, there are two special duties that it should be assigned. Number one, it should be able to receive multicast state information, the star comma G, the S comma G, from both the FHRs and the LHRs. So both the FHRs and LHRs should be able to send it this multicast state information that they've just gathered after the initial signaling. And the RP should be able to accept and should be able to process this. Why does it need to process this? That's duty number two, because it's then going to compare these pieces of information from the FHR and the LHR and work to connect those FHRs and LHRs if need be. And why would they need to be connected? Well, very simple. The FHR has information about a group, G, that the LHR needs the stream from, star comma G. So if those two pieces of information match, then the FHR needs to be connected to the LHR and the RP should proceed. Now the biggest, most important point here. The FHR, the LHR, and all of the other routers, including the RP, every single router in the domain must agree on who is the RP. Because if everybody has different ideas of the RP, now you have several different central registries, and really, how do you connect them? There are advanced level concepts that do break this rule a little bit, but for the most part, for right now, for the introduction, just imagine that all of them have to agree on what is the identity or what is the IP of this RP. Now, the RP, just another multicast router. It has to be, that's the one thing you have to just coagulate in your head, that it's just another multicast router. Now, it performs these special duties, but the only stipulation is that it should be self-aware, that it should know that it is an RP. So in this case, let's choose an RP for our little network here. Oh, there you go. So it's R3. We have just tossed a coin and we have decided that R3 is going to be the RP. Well, the very first thing here to do is to inform R3 of its new duties. So you've selected R3 and you should now go and put some configuration on R3, informing it that it is now the RP for the network and it should really be a little bit more responsible, right? So time to grow up. You're not a normal router anymore, you are an RP and you have these special duties that you need to perform. Once the RP, or R3 in our case, is aware that it is an RP, it is time to inform all of our other routers about this new identity of an RP or new responsibilities that R3 has. So from R1 to R6, every single one of these routers now has to be aware that R3 is the RP. So if you need any multicast, sparse mode related duties performed for you, you must make those requests to the RP. So in our case, R1, R5, and R6, those are the most important pieces. They must know about the RP because they have to provide this S, G and star, G information over to the RP somehow. We'll discuss that. But R2, R7, and R4, the middle hop routers, they also need to be aware of the RP. So every router in this network is now aware, including the RP's self-awareness, where it knows that it is also the RP. So the very first point here is, let's connect the LHR to the RP. And how do you do that? Well, for those who have already been through the PIM Dense Mode lecture, there is that join prune message. For those who haven't, just think of a message that the LHR is going to send to the RP. So the LHR has this star, G state. And that's where it all starts. So it receives some IGMP signaling from its directly connected receivers, and it can now start the PIM signaling process. And what it's going to do is it's going to create a PIM multicast tree. The one thing to realize about PIM trees, that they are built from the leaves, so from the very outlying branches and the leaves, and they are built towards the root. So as long as the leaf is aware of the root, they can build a tree using the middle hop routers from the leaf to the root. The RP is considered to be the root for any star, G tree. So star, G tree, it's also called a rendezvous point tree, and that's PIM specific. And it may be called a shared tree, and that's more general multicast. But ultimately, it's an ASM, any source multicast tree. And RP, very conveniently, is considered to be the root of this tree. So now what can happen? Well, the LHR is a leaf of this tree. The RP is the root of this tree. So the LHR should really be able to signal the rest of the network to create a tree from itself to the RP. And for this particular reason, the LHR sends what is called a join prune message. Now, these are messages that are used for both joins and prunes in PIM. So this is exactly the same message that we dealt with in PIM Dense Mode, but this happens to be the join version of it. In PIM Dense Mode, for the most part, we were using the prune version. We were pruning ourselves from the tree. Well, right now, we are joining ourselves from the tree. One instance of this that we saw in PIM Dense Mode was the graft message, when you were grafting yourself back to the tree. There was also that PIM or the prune override that was literally just a join message. But ultimately, you're signaling the next hop routers and the next hop routers after that up to the RP that you want to be a part of this star, G tree. Now, this has to be sent somewhere. So the easiest, most convenient location for it to be sent out of, because it has to go out of an interface from the LHR, you calculate the RPF interface for the RP. Well, what would be the unicast route to that RP? And you send the message on that interface. So the RPF check is performed on the RP's IP address. You identify that interface, one single interface, and you send this PIM join on it. Now, this PIM join has a TTL of 1. So it's a hop by hop message. And it is directed towards the RP courtesy of that RPF interface. Now, the next receiving router will do the exact same thing. It'll process that particular message. It'll create whatever states have to be created, and it'll further direct it towards the RP. So this message always is traveling towards the RP till it reaches the RP, and it is directed there by each middle hop router. So each router between the LHR and the RP, it is further sending this message further and further towards the RP. Now, as each router receives this join message, and before sending it to the RP, it will also create the star, G state. Because that's the end goal. You have to create a star, G tree, and the tree is really just a collection of all of the star, G states on all of the different routers. So the tree is being built in reverse. It is being built from the leaves to the root. And for that, the interface that receives the join. So, and we'll see this on the next slide, but on the middle hop router, so the router's, let's say, next hop to the last hop router, that interface that receives the join, or the RPF interface, that will be added to the OIL, or the outgoing interface list. And the RPF interface where the router is going to further relay this particular message, so it's going to send it towards the RP, that RPF interface to the RP becomes the incoming interface, or the IIF. So both of those things combined then create this tree. So let's take a look at how this is actually going to happen. So the join prune messages ultimately have to reach the RP, and each middle hop router should have that star comma G state. So let's pay attention to R6. Let's forget about R5 for a second, and there's a good reason for it, which we'll be covering in the next lecture. But for right now, just imagine that R5 has given all of its PIM duties for this particular segment, and it has transferred them over to R6. So R6 is really the only LHR that you should worry about. Well, R6 has this state courtesy of IGMP, this light blue state. So now it can take that IGMP signaling and create PIM signaling out of that. So the green signaling here is going to be PIM signaling. And what happens next? Well, R6 is first going to find that RPF interface. So which is the interface that will easily take it towards R3? Well, wouldn't it be this upstream interface? So wouldn't it be this upstream interface? So now for this star comma G, this interface becomes the IIF, because this is your incoming interface. This is the interface where you should be expecting to receive traffic for this particular star comma G state. So this star comma G state now has an interface in the OIL, courtesy of IGMP, and it has an incoming interface. And if you remember from our multicast routing protocol lecture, these are the two pieces of information you need for every state for that tree to be complete. Well, let's move to the middle hop router, which is R4. Well, R4 is going to receive this join. It's going to process that join. And one of the very first things that it does is it creates that star comma G state. So because it is processing and it has an idea of who the RP is, and it has an idea of that it is a multicast routing or multicast router, or it does multicast routing protocol, it creates that star comma G state. But in addition to that, it is also going to, number one, the interface where it received the join, that is now added to the OIL. And it is further going to try to find a way to relay this message, right? So what is that interface? It's the RPF interface to the RP. And if you look, it is directly connected to the RP. So identifying the RPF interface is very easy. It's that one. It's the directly connected interface between R4 and the RP, which is R3. So it is going to indicate that this interface now becomes the IIF, or the incoming interface, and it is further going to relay that join message up to the RP. And the RP receives this message, and the first thing it does is it creates that star comma G state. But furthermore, it is going to do the same thing. It received a join on an interface. So that interface, once you create that star comma G state, that interface must be added to the OIL. Now there is no incoming interface on the RP, because guess what? RP is the root of this tree. So this tree really is going from R3 to R4 to R1. So if I was to actually draw this tree out, it would be from R3 to R4 to R6 and finally down to the receiver. But that's the tree. That is your star comma G rendezvous point tree. And now you know why it is called a rendezvous point tree. So if you look up here, it has several different names. And one of those is the RP tree. And that's really the name you should be using if you're just concentrating on PIM Sparse Mode, because yeah, it is a shared tree, it's a star comma G tree, that's probably also important, but it is really the rendezvous point tree. So right now we have one leg of the tree. We have connected really the LHR to the RP by courtesy of this join prune message, and R4 is aware, and this tree, this shared tree, is now ready to carry some traffic. Now it's time for the FHR to actually connect also to the RP. But the FHR really cannot use that join prune message, can it? Because where does the join prune message go? The join prune message goes from the leaves to the root. And that's how, LHR actually joined the tree, and that's how we did it in PIM Dense Mode. But this, if you look at it and if you think about it, this is not really a good solution for connecting the FHR, or basically getting the information about the sources, to the RP. Because, yes, this join prune message was designed to build the tree from the leaves. So build the tree from the leaves towards the root. So message is sent upstream. Well, the source, where does the source sit? Doesn't the source already sit at the root? So that S comma G tree, it is, the LHR really is the root of that tree. So it is already at the top of the stream, and there is nowhere further to send the message up. So really, you would not be able to use a join prune message for this particular source signaling. So how does the signaling actually happen? Think of this scenario. So what if the FHR, it simply took all of the information that it had about that S comma G tree, and it informed the RP about the stream. So all it tells the RP is that, so it informs the RP, and it tells it that, hey, there is a source that is connected to me that is sending on this group, i.e. there is an S comma G state that I have created. Don't you think once the RP has information about this S and this G, it can then use its own join prune message? So this source sits at the root of the tree. RP can then become the leaf of that tree, and it can use this join prune message, the mechanism, and it can build a tree from itself to the source. So itself, the RP being the leaf of this tree, and the source being the root of this tree. Furthermore, the RP would build this on an as-needed basis. So it would not build this tree if it doesn't require that stream. So, and how would it know it requires that stream? Well, star comma G joins that are coming from the LHRs. So the RP would not have to build trees to sources that have groups that no receivers are interested in. So build trees from the RP to the source only for the groups that have interested receiver. So how do you bring this about? Well, there is a special message called the PIM Register message. This is literally type 1. The type of the PIM Register message is 1. And it is one of the very few unicast messages in PIM. And we'll see how that actually helps us, how this message being unicast actually helps us. So if it's a unicast message, it has to have a source IP. Well, that's very simple. If it's the FHR's IP, the first hop router's IP. What is the destination? Well, where do you want to go? You want to go to the RP, right? So the destination is simply the RP's unicast IP. So you unicast it over there. And finally, what are the contents? Well, there are a few other things, but the most important content here is this S comma G state. So you have to inform the RP about the S comma G so it can start the tree building process if necessary. But ultimately, the most important piece of information here is the S comma G. For those people who have dabbled in register messages before, don't worry, I'm going to cover them in a lot of detail in one of the future lectures. But right now, S comma G is what you should really concentrate on. So here we go. This is our state of our tree so far. So we have a source that has signaled the FHR. We have a receiver that has signaled the LHR. The LHR has also built a star comma G tree or an RP tree all the way to R3, which is the RP. So next thing now, the FHR is going to send a unicast register message to the RP. So here goes that message. And notice how that message, because it's unicast, it is literally just passing through R2. R2 has no interest in that message because there's no router alert option set in there or anything. So only the recipient may process that message. So that means any of the middle hop routers, they will simply route or forward this message as if it was any other unicast packet. They would not look at the contents of that packet. So it bears repeating, this message is not processed by the FHRs or the middle hop routers. So right now, if you look at that S comma G state, because the message is unicast, that S comma G state appears at two places. So it is on R1 because it is really it's a first hop router, and it is orange because it was generated courtesy of this multicast traffic. Once you send this PIM register message over to the RP is also going to create a state because it's going to process that message. The message has the S comma G information in it. And it is now going to create a PIM state. So this first state is really on R1 is a data plane state, but the state on the RP is really a PIM state. So that, just look at the difference in the color. This is a PIM state because it was created as a result of the PIM message. Now with this S comma G state, you are going to take the RP really is going to take a look at this S, and it is going to perform an RPF check on this S. So this S right here, the RP is going to take a look at it. It's going to create an RPF check on it and find out an RPF interface. That RPF interface, so the tree is really not built yet, but that RPF interface for this S comma G state really on R3 then becomes the IIF for this state. For this S comma G state, you right now just have an IIF. You have no oil, so you just receive traffic on it, and we'll see what you do with that traffic later. And really, you're not building anything yet, so there's nothing to be done yet. There's an S comma G state on R1. Because of the data plane traffic, there's an S comma G state on R3 or the RP, which is because of that PIM register message. And this is literally what our network looks like right now. There's nothing else going on here. Now let's come to the RP's duties. What does it do? So the recap of the situation so far, RP has a star comma G state, right? So it is at top of that rendezvous point tree. And because it is the root of that tree. So it has a star comma G state. Because it is the root of that tree, and there is no traffic yet on this tree because you just recently in the last slide discovered a source. So there's no traffic yet. The RP also knows about an S comma G state. And this happened because of that register message that came from the FHR. And it bears repeating again, only the FHR and the RP have this information. Only the FHR and the RP, no other routers in the network are aware of this particular S comma G state. The RP now will correlate the two pieces of information. So it'll compare the S comma G state and the star comma G state. And now it knows because of this G. So because of, in this case, G is not really just a variable, it actually holds the same group. So think about it like that. But because of this G being similar or the same identical group or the same multicast address across both of those trees, the star comma G tree and the S comma G tree, the RP now knows that it must relay packets that it receives on the S comma G tree. So first it has to receive those packets, and we'll see. But it must relay any packets that it receives on the S comma G tree, and it must relay them onto the star comma G tree because there are interested receivers. And if this is not gelling yet, just give it a little bit more time. Let's go through the lecture, and by the end of it, I think you'll feel much better about it. Now, RP will perform an on-demand join. So RP has an interested receiver. Remember, it has that star comma G state. And it has information about this S comma G state, but it really needs to join that shortest path tree to actually receive the packets. So remember, only the FHR and the RP have this S comma G state. So for the RP, it really must do an on-demand join to that shortest path tree to first receive the multicast packets. It must request those multicast packets to come from the actual FHR. And how do you do that? You actually build a multicast tree for those messages to fall over. Now, there are some optimizations that are built into the register message, but don't worry about them right now. For as much as you're concerned, there is no traffic yet. There's no traffic till you build a tree. So it can use this join prune mechanism because it knows about that root of the tree. So it can use the join prune mechanism to attach itself to the root of the tree. So FHR is considered to be the root of this S comma G tree, the source tree or the shortest path tree. The RP will send that join prune message. So once again, this is the join version of that join prune message. And remember how we identified an IIF, or the incoming interface, for the source on that last slide? This message is sent upstream on that IIF. So it is simply just the RPF interface on the RP for the source. Once again, this is processed hop by hop. Now the middle hop routers are actually going to process it. And it is directed towards the FHR from every router, the middle hop router. Now those middle hop routers that were, before this, they really didn't have an idea of the S comma G state. Now they can actually go ahead and create this S comma G state, because now there is actual PIM signaling that is happening for this S comma G state. Again, the tree is being built in reverse. It is being built from the leaf to the root. And the interface that receives the join, this is literally the same as that star comma G join. The interface that will receive the join, that is included in the outgoing interface list. So that now becomes the part of the oil. And the RPF interface on each middle hop router, that is for the FHR or the source, it should be one and the same thing. That is now considered to be the IIF for this star comma G state. Let's take a look at this in action. So once again, let's recap. The RP needs to join this S comma G tree to the star comma G tree because it needs those packets to flow from the S comma G onto the star comma G. And it sends that join prune message towards the source. So R3 is going to send a join prune message to the actual source for the S comma G. So now, if you realize, the color here changed. So the S comma G, pay attention to it. There we go. It changes now that state to a signaling state. So it was basically just a state created by a register message before when it was yellow. Now, because you're actually doing, R3 is actually doing some join prune signaling for it, it becomes part of that PIM join. It's a very subtle difference, but it's a difference nonetheless, because now it'll actually have an IIF and it'll actually have an actual state for it in PIM. So it's not just a result of a register message. So first of all, for that S comma G state, you actually do a RPF check. So in that RPF check should be towards the S or towards the LHR. And that then becomes your IIF. So once you have the IIF, the next thing to do is just to send the message upstream. So this burgundy message is in S, G join. So this is not a star, G join, which is the green in our network, but this is an S, G join. R2 is now going to process this S, G join because this is a hop by hop message. And R2 is going to do two things. It's first going to create this S, G state because it didn't have this before, not in our network it didn't. And it is also going to take this interface where the message was received and add it to the oil. This is added to the outgoing interface list. Now it's actually going to do an RPF check, just like R3 did. It's going to find an interface that takes it towards the source, which should be this interface towards the LHR if everything is working right in our network. And this is now considered to be the IIF. So now you have a complete S, G state because those are the three things you need. You need the state, you need the IIF, you need the oil, and you have all three of those on R2. So R2 can now send this message further upstream to R1. And R1 already has that S, G state. So it's in kind of like limbo. It wasn't really signaled. It was really learned in data plane. So I didn't know whether to leave it orange or whether to leave it in burgundy. But, you know, whichever color makes sense to you, go with that. But that state just exists there already. And it was courtesy of the data plane. And all R1 has to do is to add this receiving interface into the oil. So now you have a complete tree that goes from R3 to R1. And if you were really looking at this tree, so let's give it the color green, why not? Or blue, we haven't used that. So from R3, because of all of these states and all of this signaling, the S, G tree looks like this. So we already had a star, G tree, and now we have this S, G tree. So now it's actually time to bring those packets from the source to the receiver. So now the S, G tree is built completely, right? So from the RP to the FHR, it's actually built. The MHRs also have, you know, they've received those packets and they also have the state. So what is the first thing that the FHR actually does? It can now, because it has an oil, so that's the important part, right? That's the part that S, G signaling from the RP actually accomplished. It has allowed the FHR to add an oil to the S, G state. So the S, G state before this only had an incoming interface to the source, now has an oil. And finally, the FHR can start replicating the S, G packets. And it is replicating it on that oil. Well, that oil is connected to the MHR, right? So the MHR will receive these packets. The middle hop routers, they should be receiving it on their IIF if the tree was built correctly. They also put this through the RPF check. Once again, if the tree was built correctly, the packets should pass the RPF check. And the MHRs can further replicate them down on the oil. So receive it on the IIF, replicate it on the oil. That's what we learned so far in multicast. The packets eventually, hop by hop, going through all of the MHRs that have those states, they will eventually reach the RP. Now the RP realizes that it built that S, G. So if it's not apparent, these packets are coming down the S, G tree. And the RP built that S, G tree for a specific reason. It built it because it had a star, G state. So now the RP can replicate those packets received on the S, G on the star, G tree. And now that same process, because the packets are now traveling down the star, G tree, that same process as above, take the packet on the IIF, replicate them on the oil, can happen on the middle hop routers that are sitting between the RP and the LHR. So really the star, G tree is also replicating these packets now. Finally, we have accomplished our mission. The LHR receives these packets and now it can really deliver them to the recipients. So that was our whole purpose, and we seem to have satisfied it. So let's take a look at this in action. So the RP is now going to start replicating this traffic. So RP is going to send the traffic from, the LHR or the FHR, the first hop router R1 is going to replicate these packets and it sends them to R2. R2 performs an RPF check, sends it over to R3. Now at R3 is the leaf of this S, G tree. And that's very important to realize here that RP really, this is the end of the line for the S, G tree. So for the S, G tree, the RP happens to be a leaf. So it has to process this traffic. And what it does, the RP, is that it processes this traffic on the S, G tree. It now knows that the traffic received on the S, G must be relayed on the star, G. So that's what it does. It copies that traffic from the S, G tree to the star, G tree. So the star, G tree can start relaying this traffic on its OIL. Now this whole circular thing is implemented in hardware and there's really no processing of the traffic in any general sense. There are forwarding states that are built according to this information, but this is the mechanism of the protocol. So once again, receive the traffic from R2, process it on the S, G. And because it's on the S, G, it needs to now be sent down the star, G. So this is the trees being connected. This is the shared tree being connected to the source tree. And now because those packets have been accepted on the shared tree, send them down the OIL. If you send them down the OIL, R4 is going to receive it on the IIF, send it down on its OIL, which is towards R6. R6 is going to receive it on the IIF and send it down to the receiver. So now you can see we have actually accomplished our mission. The multicast traffic is flowing from the source to the receiver. And this is the basic crux of PIM Sparse Mode. Connecting, so building those S, G trees, building the star, G trees, the FHR informing the RP about its existence or about the existence of an S, G, and the RP finally working to connect the S, G to the star, G. This is basically the 10,000 foot view. So very high level view, but it's very important to assimilate this in your head before you move on to the next lecture, because the next lecture is actually going to deal with the details of the PIM join prune message or the star, G join prune message or the S, G join prune message or what the actual register message looks like. But really, if you go over this lecture and this all gels in your head and you can finally create this tree by yourself, I would say that you're ready to move on to the next lecture. As for this lecture, I really hope you've enjoyed it and I hope you continue on to the next lecture. Till then, thank you.